Assalamu alaikum warahmatullahi wabarakatuh. We continue with the application of the first order linear differential equation. The last time we discussed the growth problems and also the orthogonal trajectories. Today we are going to discuss the decay problem and also Newton law of cooling. So inshallah we will give you the example, also explain. We are taking the a radioactive material. Radioactive material is the material who's continuously decaying, and especially when, for example, you read in the newspaper, you get some fossil and they calculate the age of the area. They say the age of the area is 25,000 years before. How they are going to? They calculate the carbon which is left in the fossil, and with the help of in the bone, and then with the help of that one, they are able to calculate the age of that bone, and they say this area is that much old. So that's the radioactive activity, which is the mass is losing, the carbon is losing its mass. So here we are having the rate of decay is directly proportional to the amount present. This is rule number 1, which we say. Then this important concept is the half-life. What is the half-life? Half-life is the time necessary for half of the radioactive material to decay. So that's we say the half of life, and we take how much material is decaying. If this is 100 milligram, as a decay to 50 milligram, we say we want to find the half-life. It means we want to find the time when the 100 milligram will change it to, will decay to 50 milligram. So we use this one and we say if yt is the amount of the material present at any time t, then we have the rate of decay, that's dy by dt. Y is decaying. Proportional to the quantity present, we say y is the quantity present. So dy by dt is proportional to y. We change this one equation as we did before. We write here dy by dt is equal to k time y. We say k is constant of proportionality. So now we want to solve this equation, and we use separation of variable. We can write here dy by or y is equal to k dt. Variable is separated. We take the integration of both the sides, integral k dt. So we get here ln of y is equal to kt plus ln of c. Then we simplify this one, we get here y is equal to c e to power k t, and we say this is my general solution because we are having the constant of integration here, c and kt. This is my equation 1, and this is my general solution. So to find the complete solution, we need to find two values. We want to find k and we want to find c. To find c, we need condition. We say we need initial condition, and we are given information that at t equal to 0, we have t equal to 0, the amount present y equal to y0. I would say y at 0 is equal to y0. This is here. Number 2, we are having the initial condition. So when we use the initial condition, we get the particular solution. We need to find the complete solution, we need to find k. So we need one more condition to find k. To find k, we have another condition that at t equal to t1, y is equal to y1, or we say y at t equal to 1 is equal to y1. This is my condition 3. So when I use condition 2, I get the constant of integration, and when I take condition 3, I'll get the value of k, and when I know c and k, I get the complete solution, and after that I can solve my problem. So I give you the example, and we explain you that how we can apply our formula and our idea of radioactive substance. We're given only this information, that material is radioactive material. We give the information that immediately we can apply our mind that if it is a radioactive material, then the rate of decay is proportional to the quantity present directly. We need not to think that some information, additional information given in the question. So if this information is sufficient. Number 2, when you say the half-life, it means if the quantity is given, then we say y by 2. Why is the quantity given? We want to find the time when the quantity will decrease to y by 2. So then we just make the calculation and we can solve it. So I apply this one and give you an example. I'm going to give you the example for the radioactive material to decay. In this example, we have radioactive material. It having initial mass of 100 milligram. After 2 years, it's left to 75 milligram. Now we want to find the amount of material. Number one, we have to find the amount of material at any time t, and number two, we want to find what is the period of the half of the half time. Now when you want to find the solution, as I said, it's radioactive material, so some things come immediately in our mind. That the rate of decay where material is y is proportional to y, or we say dy by dt is equal to ky, and we solve it, get y is equal to c e to power kt, and this is, as I discussed before, this is my general solution. Now to find the complete solution, I need two conditions. So we can see here given to me the initial mass, initial mean at t equal to 0. So we have the conditions we are having here. So the first one is our initial condition. To find, with the help of initial condition, we are able to find our constant of integration. We are having here y at t equal to 0 is equal to 100. This is the condition given to us. That the initial mass given to us is 100 milligram. After 2 years, that's number one, condition one. The condition two, the additional condition that help us to find the value of k, and this additional condition is that after 2 years, that y2 we are left with here 75 milligram. So these are the two conditions we have. With the help of these two conditions, we try to find the complete solution. First, I take the condition 1. I take here this my number 2. That's my number 3. We take number 2. We take t equal to 0. We get here c e to power 0 is equal to y. When t equal to 0, y is equal to 100. So we get the value of c is equal to 100. We substitute the value of c in number 1. We get here y is equal to 100 e to power kt. This is number 4. And this is my particular solution. Because now this solution is not having the arbitrary constant. Now I take my condition 3, the additional condition, to find the value of k. And this say when t is equal to 2, we're having y equal to 75. I write here also when t equal to 2, y is equal to 100. So we take in equation 4, t equal to 2, we get here 100 e to power 2k is equal to 75. I get here e to power 2k is equal to 75 or 100 is equal to 0.75. I will say here 2k, we take ln of both the side, is ln of 0.75, and my k is equal to 1 by 2 ln of 0.75. We make the calculation of this one, and we can write the value of this one. We get here the value of this is minus point is equal to minus 0.1438. I told you, if in our solution this k is bigger than 0, is positive, we have the growth, and k is less than 0, we have the decay. If you remember, we have the figure like this one, and this figure is my y-axis, this is my y-axis, my x-axis. Here is k is less than 0, and the quantity is decaying. So I can write the value of k in my equation 4. I can get y is equal to 100 e to power minus 0.1438 t. This is my equation number 5, and this is my complete solution. Complete solution of the problem. Now I can just want to find I can just find number 1, number 2, and this is actually my number equation 5 is my solution. It's complete solution. Number 5 is the amount of material at any time t, amount of material at any time t, amount of material at any time t is given by this y is equal to 100 e to power minus 0.1438 t. So this is here my number 1, the part 1 of my solution. Now I go to part 2. This was number 1. So part 2 is find the period of the half-life. So when I say the period of the half-life, what does it mean? It means the time for the half of the material to decay. So what's the material? Material is 70 milligram. So we say when it's left 50 milligram. So we want to find T is number 2 when T is unknown and our Y is equal to 50 mg. So we substitute in number 5 from equation 5. We can have here this value is equal to my 100 e to power minus 0.1438 T is equal to 70 is left to be 50. We're having here this equal to 50. We want to find T or Y is given to us. So we simplify this one. E to power minus 1438 T is equal to 50 or 100 and this is equal to 0.50. We take ln of both the side, we get minus 0.1438 T is equal to ln of 0.5. Our T is equal to ln of 0.5 over minus 1438. We make the calculation. We get the value of T. The value of T we are having here 4.82 years. So we say here the half-life of the substance of radioactive material is 4.82 years. So that's how we can calculate the half-life of that. And I repeat this example with you again. We're given the radioactive material and we are given the initial mass of this one, that's 100 milligram. After 2 years, we're having two years left to 75 milligram. Then we want to find the amount of material at any time t, that means the formula. And number 2, we want to find what's the period of its half-life. So the period when half-life means the y will be equal to, when the y is left to be, half of that one is 100. We get here when it will be, when we'll get this one 50 milligram. So we are having the idea as I given you that the radioactive material always the decay is proportional to the material present. We change the proportionality by k, we solve it as I solved in the beginning. So we get y equal to c e to power k. It is my general solution. But unknowns are c and k. And we need two conditions for that one. One we say c we can find from the initial condition, k we find it from the additional condition. So for our problem, we can see we're given here this initial mass is 100 milligram. That gives me the initial condition. So my initial condition y at t equal to 0 is equal to 100. So then we need one more condition, and this is my additional condition that's given to me. After 2 years, it's left to be 75 milligram. This is my second condition. So we say when t equal to 2, y is equal to 75 milligram. So I have this, this is my equation. If we say this is my problem, this is my differential equation, and this is my initial condition, and this is my additional condition, and that is my problem which I'm going to solve. So we get here the solution. I will substitute the value of c. I just take here t equal to 0, y equal to 100. I substitute here t equal to 0, e to power 0, c equal to 100. Value of c is 100. Substitute here, I get y equal to 100 e to power k. It is my particular solution. Particular solution is when I have the value of the constant, arbitrary constant. That's the particular solution. Now I want to find this k. To find this k, I use my additional condition that t equal to 2, number 3, y equal to 75. Substitute here. When t equal to 2, we get 100 e to power 2k, t is 2, is equal to 75. Solve it. We get the value of y is equal to 0.1438. It's negative. I told you when it's a decay, then k is negative. When it's growth, then k is positive. In the last lecture, we have I explained you, give the growth problem where k is bigger than 0. Here k must be less than 0 because it's decaying. So this value k is minus 0.1438. We substitute here the value of k, and then we get here this y equal to 100 e to power minus 0.43 tk, and it's our complete solution. Complete mean now we substitute the value of t, we get the value of y. Now here we want to find, actually this is my solution, the amount of material present at any time t is given by this one. So the question is number 2, half-life. What's the half-life? As I explained you, the time we want to calculate when half of the material is left, that is 50 milligram. So we substitute in number 5 here in this equation the value of y, and we get the value of, there are two unknowns. Y is unknown and t is unknown. You give the value of y, you can find the value of t. You are given the value of t, you can get the value of y. Now you can say what is the amount present after 2 years. You can say what's the amount present after 3 years, after 5 years. So you can just calculate from this one, you'll get the time for that one. You'll get here the amount which is you are required to find, you can get the time. Now half-life, mean when y is equal to 50. So we put here y equal to 50, and then we solve it. We get the value of t easily enough, 0.5 or 1.438. We solve it. We get the value of t is equal to 4.82 years. So half-life of the radioactive material is 4.82 years. We can say how much quantity will be present after 2 years. You put here t equal to 2, you can get the value of y. You can say what's the quantity present after 10 years. Put t equal to 10, you get the value of y. There's different type of questions can be asked on base of this one. Once we have the formula, we can just make different. Here half-life, we have the concept when half of the material is present. We're going to discuss very important idea, and that's given by the Newton's law of cooling. We bring the particle which is having temperature in some other surrounding, and we want to see how the temperature is changing. Temperature of the body is changing. For example, we are having a cup of tea. We bring in when we have a cup of tea, it's about 100 to 80 centigrade temperature, and we bring it to the cool place. There is temperature about 10 degrees centigrade. Then the temperature will start decreasing. We want to see how fast this temperature is decreasing. To get how fast this temperature is decreasing, we take that this temperature is the rate of change of temperature is proportional to temperature difference. For example, if I take this body, for example, I have the cup of tea having 80 degrees centigrade and bring it to it's summer, very hot summer, and bring it outside. The temperature is 40 degrees centigrade. Now the rate of change will be slow, not fast, because now the temperature difference is only 40. There when we have 10 degrees, the temperature was 70. So if I put this cup of water and cup of tea, and I'm in a hurry, I put in a fridge, and temperature is there is -4 or -10. So the temperature difference will be 90, and it is going to cool down very quickly. So that's the rate of change is proportional to the temperature difference. We take here the Ts as temperature of surrounding, because surrounding is with S, and we say Ts is temperature of surrounding, and T is temperature of the body. So difference will be T minus Ts. So we say here the time rate of change of the temperature Ts of a body at any time T is proportional to the difference T minus Ts. Well, T minus Ts is temperature between the body and the surrounding. The T is the temperature of body. This is T is temperature of body, and Ts is temperature of surrounding. So we having the difference is T minus Ts. So Tt, this rate of change of temperature is proportional to T minus Ts. We change proportionality by K. So our formula that's come to be for the Newton law of cooling, that's T dt by ds, where capital T is temperature, small t is time. So dt by dt is equal to K times T minus Ts. K is constant of proportionality, and S is constant of the surrounding. I take the general solution of this one, and then we take the particular problem and we solve that one. We're having the differential equation is T dt is equal to K T minus Ts. I take separation of variable. I get dt over T minus Ts is equal to K dt. It's my variable separable, and we can write here our solution as integrating both the sides, here with respect to capital T and here with respect to small t. And when we solve it, we get here this is ln of T minus Ts. It's not negative, always positive, and this is equal to here Kt plus ln of C. So I take ln of both the sides, simplify this one. I get here T minus Ts is equal to C e to power Kt. I say my T is equal to Ts plus C e to power Kt, and this is equation 1, is my general solution. So as I discussed the problems for the growth and for the decay, I need two conditions, one to find C, and other to find the K. To find C, we say our initial condition. So initial condition is the temperature at any initial time. So that's my initial condition. Now additional condition is one more condition I need. For example, I was saying that the temperature of the cup of tea is 80 degrees centigrade. So my time T0, the temperature is 80. So I say I measure after 5 minutes the temperature was 70. That's my additional information, additional condition. Or it was 60, or it was say 50. Then we can calculate the time is going to reach a certain temperature, or how much time it will take. Both way we can solve our problem. So the main is we need two conditions, initial condition and additional condition. I will explain you with the help of example. Again, I just check again. So we are having here the general formula for the neutral law of cooling. This is my differential equation. I want to solve it. We solve it by separation of variable. We have dt over T1 is Ts, k dt. T is the temperature, T is the time. So variables are separated. We integrate both the sides, simplify it. We get to the solution that T is equal to Ts and is equal to C e to the power kt. So to find C, we need initial condition. I say my initial condition is T at time t equal to 0 is equal to T0. To find K, I need additional condition, one more condition, and this is at any time T1. We say T at T1, the temperature is T1. So this will give me the complete solution. So I give you an example and explain you with the help of example how I apply the neutral law of cooling to predict our solution.